So let me first thank the organizers for the invitation. And this talk will be about joint work with Luca Benini. So Luca is a PhD student of Paul Bourgade and myself, and is almost a former PhD student. So first, I apologize because this talk has almost nothing to do with geometry, integrable probabilities, and mathematical physics. This will be related to machine learning. So I hope there are some connections, and I will try to say determinantal twice. I will first begin with some motivation from machine learning, and I don't know much, but I will try to explain what we understood about this question and give you some simple first results about nonlinear random matrix models. So, okay, so we start with the modelization of a neural network. So there is an input column vector x with dimension n, and it goes through the neural network, a first layer of a neural network, and the output is a combination of some linear functional and some non-linear functional. So we are given two matrices, W1 and W2, and there is this first linear transformation, another one here, but the important thing is that you apply pointwise a function f, which is nonlinear. So the basic example, which is known in this field as ReLU, activation function, is simply the maximal function. There is a threshold. Below 0, the neuron is non-activated, and above, there is activation. Okay. Usually one has a multi-stage architecture, so you alternate layers with both linear and non-linear functionals and go through a certain number of neuron layers. Okay? So in this field, learning means that some neurons are strengthened when you learn, and one tries to mimic this fact in artificial neural network. So this time we are given an input data set and a target data set, and we try to learn the synaptic rates. So we aim to learn these rate matrices. And for this, there are different methods, such as stochastic gradient method and so on. And the thing is, you want to learn fast, so you have to make a choice for the activation function. So, as I said before, the max function is quite commonly used. This is a good one in general. So I don't know why, but it accelerates learning. And some other functions are the sigmoid functions and so on. There are plenty of choices, and you have to make the good one so that it indeed works. So now random matrices can be used in these neural networks. as I'm going to explain now, so this time we consider a matrix input data set. So this matrix will be n times p, and as usual, n and p will be both quite large. Y will be the target data set, and W, which is the rate matrix, will be random. So for ease, we assume it has i.i.d. entries. And then given x and y, one tries to estimate the target thanks to the output of the neural network through a regression estimator. This is the Z here, which is a matrix. Okay, and the aim is here to minimize the error you make using Z instead of the target Y. Okay, so this is the mean square error with a regularization factor gamma here to take into account the Frobenius norm of B. And after some computations, the optimal B is given by this matrix. Okay, so it's a formula which also arises in communication theory, and of particular importance is this, which measures the performance of learning here, and which is related to actually the Stieltjes transform of a sample covariance matrix. Okay, so this is related to this sample covariance matrix where M is just f of Wx, okay, for the activation function f.
So, excuse me, Sandrine, I'm confused a little bit by your notation. What is y small sub I?
Y small sub I.
In previous slide, yes, in fact, minimize blah 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 y small sub I in the A.
Oh, this is the column vector. The coordinate.
The square means
oh, yeah.
square of norm.
Yeah,
so
this is not a bracket.
So bracket is in fact
a norm.
Okay, thank you very much.
Okay, sorry. So there is this result from Luar, Liao, and Couillet, who have shown the following. So assume that W has subGaussian tails and F is Lipschitz continuous. And all the dimensions of the considered matrix, input data set and output, grow in the same way. Okay, so that the ratios converge to some limit. Then the empirical eigenvalue distribution of this nonlinear sample covariance matrix has the same weak limit as another kind of empirical eigenvalue distribution, and actually it satisfies a fixed point equation through its Stieltjes transform. So this is a rather complicated equation, but let me first comment this thing. So actually this is not a new equation in random matrix theory. So call Gbar the expected value of the sample covariance matrix. Okay, this distribution, this limiting distribution, is the same as that of a usual sample covariance matrix when the sample covariance is Gbar. Okay, and this is this equation is actually the deterministic equivalent of this limiting empirical eigenvalue distribution. Okay, a few more comments. In this equation, the dependence in F is hidden in this expected value Gbar, actually. And it's not obvious, but this limit is actually non-universal. And Luar, Liao, and Couillet have used this non-universality, and especially the impact on of the force moment of the distribution to improve the choice of the activation functions for learning tasks. Okay. Then there was another model which has been proposed by Pennington and Vora, who consider the following. So instead of a single random matrix, which is the rate matrix, they consider the case where everything is random. So W, the input data set, and the target data set are all i.i.d. random matrices with Gaussian entries. Okay, so for ease, I will assume that they are normalized. Actually, their result is for an arbitrary variance, but this is of no interest for the result. Okay, so again, they consider this nonlinear random matrix model. I recall that F is applied pointwise, and form the matrix, the sample matrix, 1 over P M star M, and they want to solve the same minimization problem with the mean square error. Okay, and we have a similar statement. The performance of learning depends on the asymptotic empirical eigenvalue distribution of this matrix G. And they prove the following. They prove that there exists a limiting distribution mu f, provided m over n converges to some constant phi, and m over p converges to a constant phi. And they also show that the still-just transform mu f of this distribution satisfies a quartic fixed point equation in all cases. I will come back on this result on the next slide. The way they prove it is because one knows actually one can do some computations with Gaussian matrices. Typically, the Fourier transform of Wx is known, and they use this fact with a combination of moment method to obtain this limiting distribution thanks to some saddle point argument. Okay, so we have, and actually they conjectured and made some simulations stating that this was a universal limit. And this is what we tried to show with Luca. So we need the following assumptions. So the entries W, Yj, and Xij are independent random variables which are again centered and variance 1. And we'll also assume that the tail decay is fast enough. Okay. We also make the assumption that f is a real analytic function which has an expected value 0 with respect to the Gaussian distribution. Okay, this is the same. This was also stated by Pennington and Vora. This is needed. And here, if W and X have a different variance, the variance here will be different, but this is a similar assumption. And again, the ratios of the dimension of the matrices converge to the appropriate limit. Then we can show that the empirical eigenvalue distribution of G converges to the probability distribution mu f, which is the same as Pennington and Vora. So, about this distribution mu f, actually it depends on the function f through two parameters. So theta 1 is the average of f squared with respect to the Gaussian distribution, and theta 2 is the squared average of f prime. And then we have, so this may not be so obvious, this is actually a quartic fixed point equation for the still-just transform of mu f. So we did not get a simpler expression than this one. It actually comes from the series expansion of the still-just transform thanks to moments of the distribution. Anyway, there are some rather simple cases. So this limit is universal once you fix theta 1 and theta 2. There is no strong dependence in the function f. If theta 2 is equal to 0, one recovers the Marchenko-Pastur distribution. If theta 2 is equal to theta 1, this yields a fixed point equation with degree 3, and in this case mu f is the same as the limiting distribution of a product Richard matrix, the same as if f is linear. This limit has first been computed by Dupic and Castillo in 2014. And in other cases where theta 2 is not 0 and not equal to theta 1, we get some kind of interpolation, at least as we see on moments, of such distribution. So this is important, and this is from Pennington and Vora's discussion for the choice of the activation function. Especially an important case is when one obtains the Marchenko-Pastur distribution, because it means that there is no shrinkage between the input and the output of the layer, and also that there is not too much distortion of the input data set. Okay, so here are a few plots of the eigenvalue density. So the first one is a limiting case where theta 1 is not equal to theta 2 and theta 2 is not 0. So we don't know much about the limiting distribution. It has a compact support, and that's almost all. The second case corresponds to the Marchenko-Pastur distribution. So theta 2 is equal to 0. And see the choice of the activation function. This is the case. And the last one is the case where theta 2 is equal to theta 1. And last, we can show that for such models where f is bounded, the largest eigenvalue sticks to the support of the limiting distribution. Okay. So this was the first step for learning questions, and one other question of interest is when we reinsert the data into another layer of the network. And so in principle we would expect this to happen a large number of times, but we consider the case where we reinsert the output of one layer into another layer, and this for a fixed number of iterations. Okay, so there are here L0 layers of the network, so we again consider the same matrix, except that we normalize at each step of the process the matrix so that the variance is 1 at each moment of time. So in learning, this is called batch normalization. And this is a useful thing because for learning, it helps to have some kind of isotropy for learning. And in principle, we should center here the entries of the matrix, but it turns out that this is useless for the empirical eigenvalue distribution in this setting. So we again form the sample covariance matrix MM star, and we can show that only in the case if theta 2 is equal to 0, f is again real analytic, but we need f to be bounded. Then the limiting empirical eigenvalue distribution after a finite number of layers is the Marchenko-Pastur distribution. So Marchenko-Pastur distribution is invariance when one adds some more layers of the normal networks. So all of these had been conjectured by Pennington and Vora, and this would be interesting actually to have a growing number of layers, but this we have not proved here. Okay, so I will try to give some ideas of the proof. So this is essentially a moment method, and the idea is not so complicated. So we start with a polynomial activation function f. And for ease, we assume this is an odd monomial, so that it has expected value with respect to the Gaussian distribution 0. So we want to compute the expected value of the trace of the G to some power Q. Q is fixed here. And then we make this quite awful development of the trace in terms of YL and XLJ. But we develop in all the independent random variables we consider in this problem. Okay, so I will explain first the idea. So there are some I index, J indices, and L indices here. Okay, and most of the proof lies on the encoding of the expected value of a segment in this expected value. I recall that W and X are independent. The entries are centered, so we need each of these via L to arise at least twice, so that it contributes to the expectation here. Okay, so I assume first that the Y and J's are all pairized distinct for E's, and then we encode this into this figure. Okay, so one has the Y and J indices which are distinct, so this gives a cycle of length 2Q. And then I will call the portion of the cycle between an I and a J index a niche. And we mark blue points. So a blue point is labeled with an L index, which means that we have a WY1L XLJ1, okay? So now we use the fact that each entry has to arise at least twice. So we need to match the blue point. Okay, so I used k equal to 3. So the first thing you try to do is inside a niche, you match adjacent blue points. Okay, and because k, I forgot what. Because k is odd, if you want to maximize the number of pairized distinct indices, you have to match at least one blue point with the one from an adjacent niche. So if I do, let's say this one, I match this one with this one. What will I have to? This means I have an XLJ1 which arises twice, but then the WY2L here is not matched. So, so that both W and X are matched, you actually need to make a matching with, which is a full, which goes actually along the full cycle. And all other matchings give a negligible contribution. For instance, if you match this one with this one, you lose a factor of n, actually, in the choice of indices. Okay, so this was actually the case for we had all distinct I and J indices, and we can make some more identifications within these indices. So we cannot make all possible identifications because those graphs which contribute proved to be the graphs called Cactus graphs. So essentially this means you can make I identification and J identification if the black graph you obtain is a tree of cycles. Okay, I would not make this identification in addition because this would create a cycle on my black graph, and this would imply I lose a factor of n. Cactus graphs are not new in random matrix theory. They arise, for instance, in the theory of traffics. And there is a recent article by Camille about this and some other houses and unitarily invariant random matrices ensembles. So all in all, a typical matching on such a typical black graph is the same as before. That is, there is a full blue cycle inside each of the black cycle, and then a perfect matching inside niches. Okay, so I forgot to explain one thing. Okay, where do theta 1 and theta 2 comes from? When you form this big cycle, okay, you have to determine which of the k indices you choose to belong to the big cycle in each of the niche. So this yields a factor of k. For each niche, you have k possible choices, and then inside one niche, you perform a perfect matching, which is the double factorial of k minus 1. Okay, and this is exactly the term corresponding to theta 2. And if the cycle now has a length which is equal to 2, actually you can perform a perfect matching not only inside one niche, but in the whole cycle. And this yields the factor theta 1. I hope this is clear. Okay, so we obtain the following formula for the moment, which is the same as in Pennington and Vora. So we call A of Q and some other indices the number of Cactus graph with a given number of cycles of length 2, B, which is important. And then the moment of the Q of mu F for the special choice of F, a monomial, is given here. So note that except in theta 1, theta 2, this does not depend on K. Okay. If theta 2 is equal to 0 after some computation, one recovers the number of fat trees. There are only cycles of length 2 contributing to the moment, and we get the Narayana numbers, which are the moments of the Marchenko-Pastur distribution. And if theta 1 is equal to theta 2, we simply sum with the same rate over all such graphs. Actually, B is not important here. Cycles of length 2 and longer cycles have the same weight. Okay, so we then do the same for an even monomial. I recall that we need the activation function to be centered with respect to the Gaussian distribution. So essentially, this means that we ban on any graph those matching which correspond to a perfect matching inside each niche. And then reconsider the remaining contribution, and it can only come from those graphs with cycles of length 2 only. This can be extended because the formula does not, on moments, does not depend on K, actually, except by theta 1 and theta 2 to an arbitrary polynomials. So we have to see how odd monomials and even monomials contribute, actually, and the rest is a simple Taylor expansion for the proof. Okay, for bounding the largest eigenvalue, this is because we can push the argument up to Q in the order of logarithm of n when f is bounded. And this is enough to show that the largest, using the method developed by Komlos and Furedi and Soshnikov, to show that the largest eigenvalue does not exit the support. Okay. I will now briefly explain the case of multiple layers. So multiple will be 2. We do the same. We develop the trace. So this is the same formula as before, except that run replaces the matrix X with M1. Okay, so the main difference is that M1 is still independent from W2, but the entries of M1 are not independent. Okay, so what we do is we first perform the matching for the W2 entries because they are still independent and centered, and they still have to arise at least twice in the whole expansion. And this is the matching here for the W2 entries. Okay, in the case of an odd monomial. And we do this matching, and then we forget about the indices corresponding to W2 entries. So this induces a graph on the JL entries, which means a graph on W1 and X entries. Okay, because M1 is still formed with W1 and X. So it turns out that the typical matching on W2 entries produces an admissible induced graph. This is the same as the admissible graphs we had before, a tree of cycles. And the matching on W2 entries can be as follows. So you can make a matching inside a niche, and you can also make a bridge between two adjacent niches around an I index. All other matchings, no, not all other kind of matchings will give a negligible contribution, except that you can make some identification here between bridges. And this will result into a tree of cycles for the green graph here. Okay? This is a kind of matching. So these blue matchings will create something we call flowers. Okay? So there are k-1 flowers here. And if you go through another layer of the network, the number of flowers is multiplied each time by a factor of k or k-1. Okay. So the method here really requires 2 degrees of freedom. We need 2 independent random matrices, W and X, so that it works. If one is deterministic, this is a case studied by Loire, Liao, and Couillet. This will not give a universal limit. And we also tried for a few minutes f of x when x is a Wigner matrix. It doesn't work either. This doesn't give a universal limit. This is much more complicated for the combinatorics. So probably the main problem here is that we are far from the most important activation function, which is not really real analytic. But this is a first step. Usually, one also considers complex matrices. I didn't say they are real here, but if one considers complex matrices, and F is just a polynomial, except when F is linear, one gets the Marchenko-Pastur distribution. There is absolutely no kind of other limiting distributions. This comes from the fact, if you take a Gini matrix, the second moment E of xil to the square is 0. So if you make a matching with only 2 entries, this will give 0. So you have only the contribution of cycles of length 2. So this is a funny thing, I believe. And also some questions in learning are concerned with possible outliers for this kind of models. There are some cases where in principle one could make some computation, and these are the extremal cases. So theta 2 is equal to 0 or theta 2 is equal to theta 1. So complex sample covariance matrices are complex with short. Matrices are known to give a determinantal process as well as the product of Gini ensemble. This is a result of Arnaud Kujlars and Zhang, and also Eichmann, Bourdin, and Kiburg, who have studied this question. So this could be of help to see. Well, actually, using simulations, there are some cases where there are outliers, and we have no idea of how to obtain them. And also there is a recent paper by Liu, Wang, and Wang about phase transition for the products of Gini matrices, a large product, including a growing number of products of Gini matrices, which could be of interest here, but this is for the complex case. I'm early, but I thank you for your attention.
Okay. Any questions or comments?
This combinatorial technique, do you need to have a full matrix, or could you extend also if you have kind of band matrices?
Sorry?
This combinatorial technique to determine the traces, do you need the full matrix, or you can get
full,
band
matrices?
Yeah.
We didn't try. I think I don't know. I suspect we need a full matrix because taking into account the band structure is usually more complicated, but I'm not sure. I didn't try.
Any other questions or comments?
Sorry, Jim. I missed, what does the density of eigenvalues look like if you use the max function?
I have no idea. Luca is responsible for simulations and all things like that.
And what properties of the density of eigenvalues are of interest for people who do machine learning?
Honestly, I don't really know, because I'm just beginning with learning question. I hope I get an answer within a few weeks. Sorry.
Any other questions? Okay, so let's thank the speaker.